Hey, it's Horner, and we're going to take a look at the 5.1 free response questions for momentum and impulse. Here we've got a couple of bumper cars, and several students are riding on them at the amusement park. The combined mass of car A and the occupants is 250. For car B, it's about 200. They are 15 meters away from each other, and this one is moving to the right at 2 meters per second. And they say that this car is at rest. So I think the big thing you need to do right off the bat is just put V is equal to VO is equal to, 0 meters per second for this car. And this one, the original velocity, is 2 meters per second. The first thing they want us to do is calculate if we know that this car A is accelerating at 1.5 meters per second, to a speed of 5 meters per second and then continues at a constant velocity until it strikes the car. They just want to know how much time does it take to cover that 15 meters. So let's go ahead and attack that part of the problem. We know that the final velocity should be equal to the original velocity plus acceleration times time. If I want to find out what's going on here, I know that the final velocity is 5. We're going to subtract, because we have VO on this side, our 2 meters per second. And then we want to divide by our acceleration, which is 1.5 meters per second squared. If you do that, you're going to end up with a time. So our time here is equal to 2.0 seconds. But remember, that is just the time to accelerate. Now, the next thing that we need to do is find out what distance do we go when we accelerate. So let's do that. We know that the change in position is equal to VOT plus 1/2 AT squared. So our change in position then is equal to, now remember, our original velocity here was 2 meters per second. The time that we travel is 2 plus 1/2 of our acceleration, which is 1.5 times that time squared. So that would be 2 squared. If you go through and do all of that math, you should end up with 7.0 meters as your change in position. So the next thing that we need to do is we know that it accelerates from here to here, so that's 7 meters, and it's accelerating. And then from here to here, which is the now 8 meters, we know that it's going at a V constant. It's traveling at a constant velocity. Now, how did I get that 8? Well, remember, we have 15 meters. We're going to subtract off that 7 meters that accelerate. So this is where I accelerate. And so I'm left with 8 meters of constant velocity. All right, so next thing that we need to do is figure out the time that that car travels at a constant velocity. So we know that it is going 8 meters at a constant velocity, and we know the equation for constant velocity is equal to the change in position all over the change in time. So let's go ahead and find out what is what's the time. So we need to rearrange this for time. So change in time is equal to the change in position for that constant velocity divided by the constant velocity. So we went 8 meters at a constant velocity, and we did that at 5 meters per second. So you'll notice that we're left with time here, and that is 1.6 seconds. So now we have a time to accelerate. So this is the time to accelerate. This change in time was the change in time for that constant velocity. And so if I want the total time, so time total, that's going to be equal to our time to accelerate, and so that's in this portion here, plus the time to go the constant velocity of 8 meters. We went 8 meters at a constant velocity, so that's T, constant velocity. So we're going to put delta TV there, and that is equal to 2 plus 1.6, and so our final answer here is 3.6 seconds. Where do you get points on this problem? I think that's the next thing that we need to go back and take a look at. So we get 1 point for going through and solving for the 2 seconds, but you have to show all this work. The next point is for getting the 7 meters, and so that is a point. We get 1 point for doing the math here to try to find out what's going on. You got to show all of the work. The next point is right here. So this is going through finding out how long it takes to go that constant velocity, and then summing the two together is our last point. So that is worth a bunch of points. So this is actually 1, 2, 3, 4, 5, and sometimes they will combine these 2 points. So this might actually be just worth 1 point, kind of depending on what they would do that year. For letter B, it says, after the collision, car B moves to the right at a speed of 4.8 meters per second. They want us to calculate the speed of car A after the collision. So here, this is just conservation of momentum. So we're going to use the conservation momentum equation. What kind of collision is this? So I want to know, what kind of collision is it? This collision is definitely a bounce, okay? So this one will bounce. The question is it elastic or inelastic? Well, these 99% of the time are going to be inelastic. So this one is definitely inelastic because there's probably some kinetic energy lost. So let's use our equation. The mass of cart A is the one on the left, and that is the original speed of A, plus the mass of cart B times the original speed of B is equal to the mass of cart A times the final velocity of cart A plus the mass of cart B times the final velocity of cart B. So now we can plug everything in. We know that the mass of cart A was 250. We know the velocity of cart A was 5. Velocity of cart B at the beginning was 0, so this whole thing is 0. That's equal to 250, and we're looking for the velocity of cart A, plus, and we know the mass of cart B is 200 times the final velocity of B, which was 4.8 positive meters per second, because we say to the right is positive. So we're going to take that 250 times 5. We are going to subtract the 200 times 4.8, and then we're going to divide everything that we see here by 250. Now be careful because these 250s don't cross off. You need to do the math on top. Then you can divide by 250, and that will give you an answer of 1.2 meters per second. Notice that that is a positive value. If it was negative, it would come out negative. So it says indicate the direction of car A after the collision, and that would be to the right. So let's go ahead and go back and let's make sure we know where the points are for this one. You need to have the equation and the equation filled out. So that is the conservation of momentum point, and then you get 1 point for a correct answer. You also get 1 point for saying that it goes to the right. All you had to do is check the box to get that point. They want to know, is this elastic? Is this elastic? And we said absolutely not. This one is not elastic. They do bounce. However, kinetic energy is not conserved. Well, I have to show that. So I really need to show that. Our first point comes from just clicking this. Now, let's go through and do the kinetic energy initial. So we're going to figure out what is the original kinetic energy. So I know that the total kinetic energy before the collision is equal to 1/2 of the mass of car A times its original velocity squared plus, and then 1/2 the mass of car B times its original velocity squared. But we know that this is 0 because its original velocity is 0. So we just have to do this 1/2 of 250. And then remember that this was 5 meters per second. And we're going to square that. And so here we get 3,125 joules. The kinetic energy total after the collision is going to be the sum of these two. So we have 1/2 ma v final squared plus 1/2 mb v final squared for b. This is going to be equal to 1/2 of 250 times 1.2 meters per second squared, because remember that's what we got earlier. And then to that, we're going to add 1/2 the mass of B, which is 200, times its final velocity, which is 4.8 meters per second squared. When you do all your math, you get 2,484 joules. And then this is definitely the answer. So here it says justify your answer. We really need to write in here that kinetic energy is not conserved, but momentum is. To give our basic physics, so this is our answer. Our basic physics would be K is not equal to K initial is not equal to K final, and the original momentum is equal to the final momentum in an inelastic collision. Our sight evidence is right here. It's everything we did here. And then when we draw all of this together, so when we do letter D, when we draw it all together, we just say since K is not conserved, but momentum is conserved, the collision is inelastic. You got to make sure you do all this. If you don't, you will not get full credit. Lots of you really need to make sure you're using that ABCD format. And that is the end of the very first question for 5.1.